In this video, we're going to take a look at how to solve motion problems, also sometimes called uniform motion word problems. The good thing is basically you're always going to be using the fact that distance equals your rate times your time. So most times, if you're going to set up the information in a chart, which some people like to use a chart format, some people just use more of the fact that rate times time would equal distance. You're pretty much always going to use the distances to write an equation, but for these types of problems, it's essential that you understand what's happening with the movement. What direction are people going into? What distances are equal to what distances? There are three main types of word problems, categories of motion problems. The first type is when you have motion where the two objects are headed in the same direction. The second is when you have motion in opposite directions. And the third is anytime you have a round trip happening. And so let's begin by looking at an example of each of them. Okay. So our first example is something of motion in the same direction. So Jason and Leroy entered in a 26-mile marathon. So this is the total distance that they're each going to travel. They're each trying to go from point A to point B, which is 26 miles. Okay. Jason's pace, which we're going to do in black is going to be Jason, is 6 miles per hour. So Jason is going to run this at 6 miles per hour. Okay. Leroy's average pace, which I'm going to do in blue, is 8 miles per hour. Okay. So if you're looking at this, who's going to finish the race first? Okay. Especially when it says that they're going to start at the same time. Who's going to finish first? Well, Leroy is. He's traveling faster. So I can use a chart where I have rate times time is going to equal distance. And I'm going to set up the chart, okay, where I have Jason and Leroy. The total distance is 26 miles. Okay, so I'm just going to put that down there to kind of remember that. Jason's rate is 6 miles per hour. Leroy's is 8. Since they are leaving at the same time, they're going to be traveling for the same amount of time. So Jason is going to travel 6t. Leroy is going to travel 8t. Okay. So at this point, it's going to be important to kind of think that what's going to end up happening is Leroy is going to finish. Jason will be somewhere here. Okay. Your job is to find what is this distance here. Okay. So, to keep this in mind, what's important to figure out is what's the time that they're going to be traveling. So, if Leroy travels 8 miles per hour times the time, I want to know how long is he traveling to finish this in the 26 miles. So I'm going to divide by 8. So my time will equal basically 4.25 hours. Okay. This is important to know that that's the time it takes him to finish the distance, okay, or finish the 26 miles. Jason, at that point, if he's traveling for the same amount, Jason will travel 6 times 4.25. I'm sorry, this should end up being 3.25 hours. If I can do my math right. Okay. So if I do Jason being 6 times 3.25, so I get 18. Is going to be 19 and a half miles. So how far is he from the finish line? Well, if I do 26 minus 9.5, I'm going to be left with 6.5 miles away from the finish line. Okay, so as you can see, there's not a straight equation other than rate times time equals distance. you're generally going to work something with the distance, but each problem is a little unique. So it's important that you have a clear understanding of what's going on with the motion. That's why I particularly like doing a little drawing with the arrows, just to help me keep in mind what is the different distances. Now let's take another look at a different type of motion problem. In this case, we're looking at two people going in different directions. Okay, so we say that Dan and Emily are truck drivers. Dan, which we're going to show in green, is averaging 55 miles an hour, beginning a 280-mile trip. That's going to be the total distance. From their company's Norfolk warehouse, beginning at 7 a.m. Emily, which we're going to show in red, sets out from the Charlotte warehouse at 8 a.m. on the same day as Dan and travels 45 miles per hour in the opposite direction as Dan. Then asks how many hours will Emily have been driving when she and Dan pass each other. Okay, so basically what is happening in this problem is that we have the distance from Norfolk to Charlotte. Okay, we know that this distance is going to be 280 miles. Okay, from one city to another. What's happening is Dan is setting out from Norfolk, going towards Charlotte at 55 miles per hour. And he's going to leave at 7 a.m. Charlotte, Emily, leaving from Charlotte, is going to go towards Norfolk, going 45 miles per hour, and she leaves an hour later, so at 8 a.m. Okay. We want to know basically what happens when they meet, which is going to be somewhere in the middle, a little bit closer to Charlotte because Emily's driving more slowly, and she's leaving later. So how do I put this in sort of my table? Okay. Well, I'm going to have Dan, and I'm going to have Emily. Okay. I'm going to have my rate times my time is going to equal my distance. Okay. And I know my total distance somehow is 280 miles. Okay, that's sort of the distance from one city to another. If I fill in the information, Dan is at 55 miles per hour. He leaves at 7 a.m. Now be careful. Even though this is a time, it doesn't tell how long he's been traveling for. He just leaves at 7 a.m., is traveling for, 4, 5, 6 hours, I don't know. So I'm going to call the time he's traveling T hours. He's leaving at 7, traveling for T hours. That's the amount of time he is traveling. So the distance will end up being 55 T that he travels. Emily, on the other hand, is traveling 45 miles an hour. She's leaving at 8 a.m. Okay. Now, I really don't want to define a different variable because I don't know what the variables are, okay, or in terms of time. It's really going to be difficult to write two different sets of equations. But what I know is that if she is traveling an hour later, okay, when she leaves at 8 a.m., Dan's already been traveling an hour. So Emily's going to travel T minus 1 hour. Okay, even though she's leaving an hour later, she's traveling for an hour less, which makes that difference why I am subtracting. Because the actual travel time is less, and that's what T stands for. So her time is going to be 45 times T minus 1. Okay. Now if I follow up these arrows and look at what distances are going to be equivalent, because most of my equations come from distances, I'm going to know that Dan's 55T that he travels, the green arrow here, okay, plus the red arrow, which is this distance of 45 times T minus 1, is going to equal this total distance from Norfolk to Charlotte. In other words, 280 miles. Okay. If I distribute, okay, I get 55T plus 45T minus 45 is equal to 280. Okay. 55 plus 45 ends up giving me 100t. If I add 45, it's going to equal 325. Okay. At this point, I'm going to need to divide by 100. Okay. So my time will be 3 1/4 hours. 3 1/4 hours. Okay. That tells me what the t is. I need to make sure I go back to my chart. That tells me how long Deanna has been traveling, but the question says, how many hours will Emily have been driving? It's going to be crucial that you make sure you are answering the correct question. At this point, Deanna would have been traveling 3 1/4 hours. Emily travels for an hour less. So Emily travels for 2 1/4 hours. In other words, 2 hours and 15 minutes. Okay. So I think you're probably beginning to see these types of problems are pretty challenging. Once again, what's essential is this little diagram, I think, in helping you to figure out who's going in what direction, what distances are equivalent to be able to put into these equations to solve. Our final type of problem is what's called a round trip problem. Okay. The good thing is when it's round trip, we're looking at leaving a certain place, going to some place, and coming home from some place. The good thing about these types of round trip problems is usually the distance it takes to get someplace is equal to the distance getting home from that place. So the chart is usually to and from. We have, I'm going to set up my chart with my rate times my time will equal my distance. Okay. And then I read the problem. A family drives from their home to an amusement park. So in this case, it's home to the amusement park at an average speed of 50 miles per hour. So going to the amusement park, they're traveling at 50 miles per hour. The return trip is made at an average of 60 miles per hour. So that's going to be going back. The trip from the amusement park is going to be 60 miles per hour. The trip home took 15 minutes less time than the trip to the park. So if it took t hours to get to the park, it's going to take 15 minutes less. Now what's going to be important here is since I'm giving the time in miles per hour, I can't have minutes. I need to know that 15 minutes is going to be the same thing as a quarter hour. So I'm going to need to use this 1/4 hour as opposed to using 15. So it took 15 minutes less, a quarter of an hour less time. So if I multiply those out together, okay, I'm going to have 50t for the distance to, and 60 times t minus 1/4 for the distance home. Now, the distance from home to the amusement park will be the same thing as going from the amusement park to the home. It's the same distance. So, like most round trip problems, my distance to is equal to my distance coming home. So if I solve, 50t is going to equal 60t minus 15. Okay. If I subtract 60t, I get negative 10t is equal to negative 15. Divide by negative 10, divide by negative 10. My time, my t, is equal to 1.5. Okay, and the negatives cancel out. So this tells me that it takes 1.5 hours to get to the amusement park, and it's going to take 1 hour and 15 minutes to get home. 1 1/4 hour to be able to get home from the amusement park. Once again, though, I've got to pay attention to what the question is asking. The question says, how far away from their home is the amusement park? I found the time it takes to get there, to get home, but I don't have a distance yet. So the distances, I can stick with the 50t. The distance is given by 50 times the time of 1.5. So in other words, it's going to be 75 miles away from the house. And I can confirm that by figuring out what 60 times 1.25 is, and that's going to give me the 75 miles as well. Okay. So once again, hopefully you're beginning to see a little bit of work with these motion problems, what are called uniform motion problems. They're not easy. They're also very difficult to teach. The best way I found is to do a little sketch, okay? But it's very important for you to get your kind of brain around what's happening with distances, where are the distances equal, and how do I turn that into an equation. Good luck.